Welcome to The Explainer. I am absolutely thrilled you're here. Today we're diving into one of the greatest cosmological mysteries right in our own celestial backyard, the space between Mars and Jupiter. If you look at a map of the solar system, it really feels like there ought to be a planet there. But instead, there's just a sprawling ring of cosmic debris. So we're going to investigate the origin of the asteroid belt, the massive forces that shaped it, and figure out exactly what happened to the planet that never was.
Why is there no planet between Mars and Jupiter? That's the central question of our cosmic crime scene today. Now, pop culture and sci-fi movies have kind of conditioned us to imagine the asteroid belt as this incredibly dense, chaotic minefield. You picture giant rocks constantly crashing into each other, right? A place where a spaceship pilot has to frantically dodge and weave just to survive. But as we'll see, the real story is far more fascinating, and it completely shatters that Hollywood illusion. To understand why there's an empty rocky ring instead of a fully formed world, we have to go all the way back to the very beginning.
Section 1. The Missing Planet Mystery.
So our story kicks off about 4.6 billion years ago. Back then, our neighborhood was basically just a gigantic, collapsing cloud of gas and dust called the solar nebula. As this cloud collapsed, the conservation of angular momentum caused it to spin faster and flatten out into a massive protoplanetary disk. Now, a super common misconception is that the asteroid belt is the wreckage of a fully formed planet that somehow exploded or maybe got smashed to pieces in some cataclysmic collision. But the evidence tells a totally different story. The asteroid belt isn't a destroyed planet at all. It's actually primordial rubble. We're talking about leftover building blocks, planetesimals, that simply never managed to finish construction.
Okay, let's dive into this number right here, because it really sets the stage. When that solar nebula collapsed, the vast majority of the mass collected right in the center to form our sun. The leftover material from the sun's formation, a mere 0.14%. And that tiny fraction is what evolved into literally everything else. That 0.14% became all the planets, all the moons, the comets, and yes, the asteroids. So right from the get-go, there was a very limited budget of building materials. And, well, one particular neighbor was about to take way more than its fair share.
Section 2. Jupiter, the planet preventer.
It all comes down to a fundamental rule of our universe. The gravity of each object pulls on every other object. And obviously, the more massive the object, the stronger the pull. Jupiter formed about 4.6 billion years ago alongside the rest of the system, but man, it took most of the mass left over after the Sun formed. In fact, Jupiter ended up with more than twice the material of all the other bodies in the solar system combined. Because it is just so incredibly massive, its gravitational field is ridiculously dominant. It essentially became the great gravitational bully of the early solar system.
And that bullying had a direct, devastating impact on the region between 2.3 and 3.3 astronomical units from the Sun. That's the area we now call the main asteroid belt. In the early days, the dust and gas here gravitationally attracted each other, coalescing to form larger and larger bodies, exactly like the rocky planets closer to the Sun did. But here, they failed to coalesce into a single major planet. Why? Because of Jupiter's immense gravitational interference. Every single time Jupiter completed an orbit, its massive gravity sent a disruptive tug right through this region, totally stirring the pot. It accelerated these planetesimals, causing them to smash into each other with way too much energy to actually stick together. So instead of merging gently into a nice new planet, they shattered. Jupiter's gravity kept the rocks as rubble.
Section 3. The Grand Tack Hypothesis.
Now we're looking at a period of sheer dynamical instability in our early solar system. Following the dissipation of the original protoplanetary disk, gravitational encounters between the remaining debris and the gas giants caused those giant planets to actually migrate. It's wild to think about, but the Grand Tack Hypothesis proposes that Jupiter originally migrated much further inward, toward the Sun. Then, caught in this complex gravitational dance with Saturn, it actually reversed course. It tacked outward, very much like a sailboat changing direction against the wind, and eventually settled into the orbit we see today.
And this brilliantly illustrates why the asteroid belt is the way it is today. Imagine a massive snowplow driving straight through a field of loose gravel, and then just backing up right over it again. As Jupiter plowed inward and then outward, its massive gravity scattered those planetesimals absolutely everywhere. It dispersed a huge amount of the original mass of the asteroid belt, flinging icy bodies and rocks in all directions. In fact, this migration is thought to have triggered the late heavy bombardment. That was a rough period where the inner rocky planets, Earth included, were just pummeled by this scattered debris. Jupiter quite literally rewrote the architecture of our cosmic neighborhood.
Section 4. Resonances and Kirkwood gaps.
Which brings us perfectly to orbital resonance.
In celestial mechanics, orbital resonance happens when orbiting bodies exert a regular periodic gravitational influence on each other. This usually occurs because their orbital periods, the time it takes to go all the way around the sun, are related by a ratio of small integers. This mathematical relationship drastically enhances the mutual gravitational influence between the bodies. Now, I know that sounds a bit abstract, but the source material actually gives us a really perfect, everyday analogy to wrap our heads around it.
Think of a child on a swing. If you just push the swing randomly, well, sometimes you help it go higher, but other times you accidentally push against its momentum and slow it down. But if you push that swing at the exact right moment, in its natural frequency, in periodic repetition, your pushes have a cumulative effect. The swing just goes higher and higher, and that is exactly what Jupiter is doing to certain asteroids. Because of orbital resonance, Jupiter gives specific asteroids a gravitational push at the exact same spot in their orbit, over and over, thousands and millions of times.
Now, what's really interesting is when you map out these specific resonant pushes, they create what we call Kirkwood gaps. Out in the asteroid belt, there are specific locations where an asteroid would orbit the Sun exactly 3 times for every 1 time Jupiter orbits. That's a 3-to-1 resonance, or maybe 2 times for every 1 of Jupiter's orbits. Because of that cumulative swing-pushing effect from Jupiter we just talked about, the asteroid's orbit gets highly eccentric and super unstable. Eventually, the asteroid is violently ejected from that lane altogether by those repeated perturbations. So the Kirkwood gaps are quite literally empty lanes swept completely clean by Jupiter's gravitational rhythm. It's fascinating.
Section 5. The Asteroid Belt Today.
Surprisingly, despite all of that ancient chaos, there are some pretty incredible survivors out there. We actually have relatively intact protoplanets. These are precursor stages to a fully formed planet, right there in the belt today. There's Ceres, which is so big at 940 kilometers in diameter that it's actually classified as a dwarf planet. It has frozen water, hydrated minerals, and even a very thin water vapor atmosphere. No joke. Then there's Vesta, which is basaltic and heavily scarred by 2 absolute giant craters named Rhea Silvia and Venenia. And there's Pallas, which is predicted to have a silicate surface. So we're not just looking at random space potatoes here. These are complex, surviving planetary embryos.
But here is the most staggering fact of the whole explainer. Despite Ceres, Vesta, Pallas, and the tens of thousands, maybe millions of other rocks out there over a kilometer in diameter, the total mass of all the asteroids combined is less than that of Earth's moon. Yep, you heard that right. If you somehow gathered up every single piece of rubble in the entire main asteroid belt and mashed it all together into a ball, it wouldn't even equal the mass of our own moon. It's likely not even 1,000th of the mass of Earth. Jupiter truly, utterly robbed this region of its potential.
So the absolute crucial point is this. The asteroid belt is definitely not a dense, chaotic minefield from a sci-fi movie. Because that tiny amount of remaining mass is spread out over an incredibly vast, torus-shaped region of space, the belt is actually mostly empty space. It's really a sparsely populated graveyard. When NASA sends spacecraft out to the outer planets, they don't have to frantically dodge rocks. They routinely fly straight through the asteroid belt without incident. It is a beautifully choreographed, very quiet memorial to the planet that never was.
Which leaves us with this final, kind of provocative thought. We know Jupiter prevented a rocky world from forming next door, and its migration hurled debris all throughout our neighborhood. But what if Jupiter had been smaller? What if it had never migrated inward in the first place? Would a massive super-Earth have formed between Mars and Jupiter? And if it had, how would its gravitational pull have changed Earth's orbit? We owe our relatively calm, stable existence right now in part to the violent, chaotic history written by Jupiter's gravity. I really hope this explainer helped you see the asteroid belt not just as a bunch of floating rocks, but as a dynamic, deeply historical piece of our solar system's puzzle. Keep learning, keep questioning, and I'll see you on the next one.